Okay, I think we can start the session. So welcome to Fundamental Aerosol Processes from Nano to Microscale. I'm Tinja Olenius from SMHI, the Swedish Meteorological and Hydrological Institute, and I'll be moderating the session. My co-chair, Chonghua Cheng from Manchester University is over there. He'll be keeping an eye on the Slido platform. So we have 4 presentations in the session. Covering topics from resolving the detailed molecular mechanisms and aerosol properties to large-scale applications. And our first speaker is Siddharth Iyer. He's an academic research fellow at the Tampere University in Finland. His research focuses on studying the gas phase oxidation chemistry of biogenic and anthropogenic hydrocarbons. And he's currently investigating the oxidation chemistry of monocyclic aromatic hydrocarbons at the Aerosol Physics Lab in Tampere. Please.
Hi, hello everyone. My name is Siddharth Iyer, and thank you for the introduction. My work primarily involves understanding the oxidation mechanisms of volatile compounds, and that is what I'll be talking to you about today. Specifically, I'll be looking at the oxidation mechanisms of alpha-pinene and also some aromatics. In my work, I mainly use computational methods, so computational quantum chemistry, and I pair that with some laboratory experiments. And that is done with a flow reactor connected to a chemical ionization mass spectrometer. And the combination of these 2 methods allows us to get a better understanding of what happens in the molecular level during oxidation. And I've changed the title a bit here. I just want to talk about 2 sort of aspects of the oxidation mechanisms that we have recently discovered, how excess energy and rule breaking can enhance auto-oxidation rates. Right, you probably have already seen this similar slides before. If we broadly classify emissions into 2 categories, anthropogenic and biogenic. Anthropogenic emissions mainly are your alpha-pinenes, or your monoterpenes and isoprene. In the urban environment, you have a lot of aromatics. And once they're released, they're oxidized in the atmosphere. And this is primarily done by atmospheric oxidants. So you have something like ozone and OH. Both ozone and OH are quite important for the oxidation of monoterpenes. But for aromatics, it's OH that dominates. And once they oxidize, so they have initial oxidation attack, they kickstart a series of reactions that very quickly lead to these condensable vapors, or these highly oxygenated organic molecules, or HOM, that you might have heard of. And these condensable vapors then lead to the formation of aerosol that affects climate and also health. My work primarily focuses on this gap between the initial oxidation attack, right, and the formation of condensable vapors. A significant process in this gap is auto-oxidation. Right? What is auto-oxidation? When a volatile organic compound is oxidized, you form a peroxy radical. This is a key oxidation intermediate, and it looks something like this. So you have a hydrocarbon, and you have this functionality, 2 O's, right? These are reactive molecules, and one way they can react is with themselves. So, for example, they can abstract an H atom from one of the carbons inside the structure, right? And they do this by going over an energy barrier, right? We call that a transition state. How quickly it does this depends on how high the transition state is. And once it does that, you have a very reactive carbon atom, right? So under atmospheric conditions, you have so much O2, very rapidly O2 adds to this, and you form a second peroxy radical. Now this in turn can again do an edge shift and add O2 and go so on and so forth. Very quickly, you get these highly functionalized oxidized products that we call HOM, right? And these are extremely important, especially in the early stages, right? When you're growing these really small particles, right? And another way of showing auto-oxidation is something like this. right, from this paper where they looked at cyclohexene oxidation. So this is, in a potential energy surface, you see how the reaction proceeds, and these little bumps, right, along the surface, that denotes these transition states. So your peroxy radical has to overcome them to form these products. And your products are always lower in energy, right? So you are forming stable products that can continue to react. And even though you have an O2 addition there, so it's sort of considered bimolecular, but given how much O2 we have in the atmosphere, we can consider this whole sequence unimolecular reactions. Right? So you have RO2 overcoming a transition state, right? And then forming a new RO2, and this process can continue a few times until you form a HOM, right? And a condensable vapor that can then directly participate in SO8. But that's not the only reaction channel available to an RO2. You already saw this in previous talks. RO2 can react with other atmospheric phase gases, especially NOx, so NO, NO2, RO2, HO2. And these reactions predominantly terminate oxidation. I say predominantly, and I'll come to, there are ways that they can continue to react. And the efficiency in forming HOM is dependent on how quick your unimolecular reactions are. If they are fast enough, you form your HOM, right? If they're slow, under atmospheric conditions, they can react with something else. And as a rule of thumb, we have something like 0.1 per second rate coefficient. I mean, this is highly dependent on the environment, but in a particularly polluted environment, if your unimolecular reaction is 0.1 per second or faster, you can be safe to assume that your oxidation dominates. Right. So when we are computing oxidation rates, we are looking at reactions that are faster than this or equal to that. And the faster your
oxidation is, right, is less susceptible the molecule is to termination, because your RO2 continues to auto-oxidize with itself. So it doesn't have a chance to meet bimolecular reaction partners to terminate it. And as a note, like I said, not all bimolecular reactions lead to termination, right? So you can form alkoxy radicals. These are reactive. They can continue to oxidize. Important to remember. And also not all termination products are volatile. So like especially these accretion products like ROOR, they can have really low volatility and participate in new particle formation. Now I will come to two cases. The first is alpha pinene. I want to talk about some previous discrepancies and how recently we've gotten to understand this mechanism better. Right, I would like to sort of guide your eyes on the right first. So these experimental results. So what we did is we used this atmospheric pressure interface mass spectrometer, a nitrate chemical ionization to ionize our sample. And we controlled the reaction time. So now this is in a flow reactor. So we controlled the amount of time alpha pinene has to interact with ozone, right? So with just 75 milliseconds, you have alpha pinene that's volatile, that has 0 oxygen atoms. It converts to a product with up to 8 oxygen atoms, right? In 75 milliseconds. So this is really fast. And when we increase the time slightly longer, at 300 milliseconds, we get up to 011, 010. Right, again, so this is known, right? Alpha pinene is a very efficient source of SOA. It forms HOM very, very quickly. But there was a gap in our understanding of the mechanism. So on the left here is what our understanding was of how alpha pinene plus ozone, the reaction proceeds. So ozone adds to the double bond, and then you have a series of reactions. You form a Krieg intermediate, and then you form something called a vinoxy radical. Right? And under atmospheric conditions, this adds an O2, and you form a peroxy radical. And now here it's a wall, because you have this ring in the middle. You have a very rigid structure. Right? If you want to have these edge shifts, you want to have a flexible structure that can efficiently pick edge atoms. And when you have a ring like that, you make this quite rigid, and that translates to higher barriers, slower rates. Right? And so these rates are much less than 0.1 per second. So now there's a mismatch between what we are measuring and how we understand this proceeds. And these mechanisms, of course, are important for our models, right? We want to get that accurate. Now I'll come to, and this is just another way of showing exactly the same thing, right? So you have alpha pinene plus ozone, and you have these different intermediates that I just showed you, right? And you have this vinoxy.
And what I want you to take away from here is that the formation of this is quite downhill in energy, right? So it's coming in with a lot of excess energy. And that's important, right? Because that enables it to go over this bump, right? It's a new reaction pathway. And this reaction pathway is important because it leads to a completely ring-broken radical, right? So you have a ring, and it can isomerize, break the ring, form a peroxide radical that's completely ring-broken. Now, this is really important because now you have a flexible peroxide radical that can do any of that shifts you want, right? And now it can proceed to form these O10, O12 products that we see. And what we noticed was, given the amount of excess energy coming in with the Vinoxy, the ring-broken product, the new product that people didn't know about, is actually the dominant product compared to the previously thought, the CbRO2, the previous peroxide radical. Right, so now we have a mechanism that's more in line with what we're measuring, and it should in principle lead to better models. And a second example, in this case, toluene, another extremely important molecule, especially in the urban environment, right? And once again, on the right, when we did flow reactor measurements, we controlled the resonance time or the reaction time to 4 seconds, and we were already able to measure 0.11, 0.09. We were able to reduce the time to sub-seconds, and again, we were able to measure products with 9 oxygen atoms. Now, when we look at the mechanism of how we understand it, on the left, it might look a bit complicated, but this is just to show you that OH, right, when it oxidizes an aromatic, it adds to it. And it can add to different carbons. So it can add to the second carbon called ortho, third, and so on. And I sort of give you a better description of the mechanism when it adds to the first carbon, or the ipso. And it, again, goes through a series of reactions, and it stops here at a BPR. This is a bicyclic peroxide radical. Bicyclic because you have the 2 cyclic rings, right? And it's important, I just want to note that ipso addition is important for the subsequent reaction that I will tell you in the next slide. But otherwise, the mechanism is identical for all the other OH addition sites. So yeah, you form the BPR, it's rigid, it can't do edge shifts again, because again, you have 2 rings now. And we again have a mismatch between how we understand the mechanism goes and what we measure. But what we found was when the ipso addition happens, that is, OH adds to this carbon with the methyl group, it can actually open up. So it opens up in 2 ways. It forms these peroxide radicals that are completely ring opened, right? And not only that, so again, now it's flexible, it can do the shifts that we want. In addition, the formation of them is quite downhill in energy, right? So again, you're forming these with excess energy. Now this is important because it doesn't just follow the path of least resistance, right? It doesn't just follow the oxidation pathway that has the least barrier. It can actually undergo multiple different edge shifts, right, simultaneously. So it can have, these are higher energy edge shifts, but the molecules can, at different yields, you can get different ratios of the different oxidation channels. And each of these channels can continue to oxidize to form your HOM. Now, this is a complicated figure, but again, just the takeaway here is that each of the differently colored arrows is a different oxidation pathway, and each step is fast, and at each step, you're adding an O2, right? So very quickly, you are forming highly oxidized molecules. So now, again, we have a better mechanism for toluene oxidation, right? And this, in principle, again, should improve our models. And that's what we saw when we use this mechanism to sort of model our flow reactor, our HOM spectra. We got a much better agreement compared to what we had, the model had before. And significantly, it's not just toluene that does that, right? The BPR intermediate is important for aromatics in general. So they go through these bicyclic peroxide radical intermediates. And for the ipso addition, for all of these different aromatics, all important, the rearrangement rate, so the rate at which it opens up, right, is close to 1 per second or faster. So this reaction is significant for aromatics, and more of them. And in addition, For example, for paraxylene, when we looked at the more detailed auto-oxidation mechanism, once it opens up, it's quite similar to that of toluene. So the main pathways, right? It's taking the same hydrogen atoms. You just have an extra methyl group that's not really doing much. So in principle, we have similar mechanisms for aromatics, right? But controlled by how much of, controlled by the molecular rearrangement rate. Now to check how good this mechanism is for different xylenes, we did experiments with the 3 different isomers of xylene. Okay, I guess the spectra is missing for some reason. Okay, there were peaks there. So, I mean, the labels will tell you how high the peaks were. I have no idea why. So what we found was for paraxylene, we found we got a lot more home, right? And for ortho and metaxylene, we got a lot less home, right? And can our mechanism explain this? Right? So what we found was the 2 columns here are, the left column is the ipso yield. So how much of the OH adds to this ipso position, that's the substituted carbon. And the second column is the rate at which it opens up. Orthoxylene has a high ipso yield. So a significant amount of OH oxidation enters it, oxidizes it by attaching to the ipso carbon. But the molecular rearrangement rate itself is quite slow. Metaxylene has a really fast a really fast molecular rearrangement rate, right? So about 3 per second or more. But the ipso yield is really, really low. Paraxylene has this balance of, it has quite significant molecular rearrangement rate of about, again, 1.5 per second, while the ipso yield is also significant, up to about 30%. So when both of them are quite significant, you have higher home yield. And so this sort of tells us if the subsequent auto-oxidation mechanism, the really complicated part, that the part where it's difficult to sort of include in models because they're so complicated, if it turns out to be identical for aromatics in general, all we need is the ipso addition yield, which is in literature, and the molecular rearrangement rate, which is trivial to calculate. Right. And also we did some SOA yield measurements in chamber experiments. And what we found was the xylene that has a higher home yield translates to higher SOA yield, SOA mass yield as well. Right? For two different reactive VOC experiments, we have higher SOA mass from chamber experiments for paraxylene compared to the other 2. So this follows, right? So this shows that it's important, which we know that HOMs are important for forming SOA. Right, to conclude, I want to say, first, getting accurate, explicit oxidation mechanisms is important for models, right? So having this peroxy radical auto-oxidation mechanism that was mentioned before in models is important to get a better understanding of SOA yield or better prediction. And this excess energy and ring breaking seems to be key for alpha-pinene. I mean, we are finally achieving this closure between measurement and our understanding of the mechanism because of accounting for excess energy, which has not been really done before, which probably should be done for other VOCs as well. And for the aromatics, it seems to be that the ipso yield and the fast molecular rearrangement rate are, and these things translate to higher home yield. And if it is just this, if you can, these things that we can easily either compute or get from literature, and the oxidation mechanism is otherwise similar, I think it helps with the mechanism, with the modeling. And yeah, and that would be the last point. Can we accurately model SOA mass yields of other aromatics based on what we know for toluene and paraxylene, for example? And that's what we're trying to find out. Right. With that, I would like to thank you for your attention. Thanks.
Hi, I'm Craig Tages, Sandia National Labs. This is very interesting, and I'm wondering how you are including or modeling the energy content of the products of these exothermic reactions as they continue to react, because that's one of the things that's very not problematic, but that's one of the really interesting complexities of modeling these chemical activation processes in a real system.
Yes, it has been quite complicated, especially for biomolecular reactions and biomolecular products. What we use is master equation modeling. So we use Messner, for example, and that is quite good at accounting for excess energy and also thermalization with collisions with the bath gas. So it is quite efficient at accounting for how the excess energy contributes to further reactions. And yes, it's not trivial, especially when you have biomolecular products, to account for when you have fragmentation, how specific fragment has enough excess energy to continue to react, for example.
How are you including that in a big mechanism to carry that excess energy through, for a complex chemical reaction system like you might use in an atmospheric chemical model?
I mean, in terms of, the mechanism itself for the alpha pinene is quite big, but that we could do. But what we could include in atmospheric models, I suppose, would be the end product, so the yields of these different products and the rate coefficients. But yeah, with alpha pinene, we were able to model for the entire potential energy surface. Yeah.
Great, thank you.
And our next speaker is Noora Hyttinen. She's a postdoctoral researcher at the University of Jyväskylä in Finland, and her work focuses on quantum chemistry-based thermodynamic properties of organic aerosol constituents. And today she'll talk about the effect of aminium salts on aerosol water uptake.
Thanks, Tinja, for the introduction. So I have been doing some quantum chemistry-based calculations on the effect of aminium salts in water uptake. So I don't know how familiar people are with hygroscopic properties of aerosols, but generally salts increase the water uptake of aerosol particles, and even small amounts of salts can dominate the hygroscopic behavior of particles. So here I have one example of this saturation ratio of different ammonium sulfate and sodium chloride particles as a function of the droplet diameter. And you can see that the critical supersaturation of cloud activation is different for these two different salts, same diameter of the particle. So this is what I want to study, if these different aminium salts also have kind of different water uptake. And I'm not exactly calculating the critical supersaturation, but just like the water uptake of the particle. I'm using computational methods in my work, and I'm calculating activity coefficients of the water using a conductor-like screening model for real solvents in the Cosmotherm program. So there I use quantum chemistry input in the model. So it's this kind of charged surfaces around the molecules, all of the molecules in the system. And then you can obtain activity coefficients of each of the compounds. And then I calculate activity of water by multiplying the activity coefficient with the mole fraction of water. And then I'm assuming that at the equilibrium, the water activity is equal to relative humidity. So then if you want to know the water content of your particle, at a specific relative humidity, you can calculate back the mole fraction of water if you know all of the activity coefficients in all of the different mixing states. So for my study, I selected different amines that have been measured in the atmosphere. So I have alkyl amines that have just like alkyl groups and one or two amine groups. Then I have guanidinos, and then also amino acids. And as the anions in the salts I'm using sulfate, bisulfate, and nitrate, iodate, and methyl sulfonate. So then I have a large collection of different, all possible pairs of these cations and anions. So here I have already the results of binary solutions. So these are water activities in the different salts as function of the salt mole fraction. And on the top row, I have all of the different bisulfate salts. And they are grouped based on the previous slides. So I had the alkylamines and then guanidinos and amino acids. And all of these water activities are quite similar if we consider the probable uncertainties of the computational method. And then if we compare with these sulfate, methyl sulfonate, and nitrate salts on the bottom row, you can see that there is some larger variation, especially in the sulfate salts. But then mostly the order of the different cations is the same in the different salts, different anions. I also drew the same figure as a function of mass fraction of the salt. So that's right. So this changes the figure a little. So here you can mainly see that the smaller aminiums have higher water uptake or lower water activity, just because they have lower molar masses. So then the amount of water mass is higher than larger amino acids or guanidinos. And I also wanted to investigate the effect of adding an organic to the mixture. So there are two different cases where one organic is hydrophilic. So it's miscible with water. So then it forms these particles that are mixed phase. So the salt, water, and organic are in one phase. Then there's the hydrophobic organic case, where the organic and water phase separate. And then when you add the salt, then the organic is even further salted out from the aqueous phase. So then the aqueous phase has almost no organic in it. And this is, in this case, because water activity is equal in both of those two phases in equilibrium, then there's basically no effect in the water content, even if we add some organic in the particle. So that's why I focus in my presentation in this hydrophilic organic. So I picked one product of isoprene, and it's this what was mentioned already in the morning, this IEPOX, which is isoprene-derived epoxydiol, which is very abundant in the atmosphere. So in this figure, I have the water content in mole fraction on the y-axis, and then on the x-axis is the mole ratio of the organic and salt in the pure particle. And then the different colored lines are showing the water content at different water activities or different relative humidities are all now methyl sulfonate salts. So I have 3 salts as an example. And here you can see that starting from the pure organic, which is 0 on the x-axis, starting to add more salt increases water content particle. And if we look at all of the salts in this scatter plot, where I have now I'm using mass fraction of water, which is kind of showing more the actual water content and not just the mole fraction water content. So in this figure, I selected 70% relative humidity. So these are then all the values where the water activity is 0.7. And on the x-axis is the water content in the pure salt. And then y-axis is water content in a mixture of salt and IEPOX with 1:1 mole ratio of the organic and the salt. And then the blue lines are showing the water content in a case that, or in particle that only contains IEPOX. So you can see that most of the salts are increasing the water content at 70% relative humidity. And especially these smaller monoamines and then diamines increase the water uptake more. And then depending on the salt, it might be the pure salt or then the salt IEPOX mixture that has the higher water content at equilibrium. And here I already have my conclusions. So aminium salts take up more water in most of the cases than the pure organic or pure hydrophilic organic. And then the smaller aminium salts lead to higher water uptake in mass fraction, but in mole fraction, there was. And then the effect of the organic depends on the solubility of the organic in the particle because of the phase separation. The article where you can go read more if you're.
So this is really interesting. And I'm curious about the outlook when you have mixed salts and or mixed organics. And if we could use the same methods, and if you have any idea of what might happen or how this sort of holds up, how, do we have linear addition or what happens?
Yeah, I haven't tried mixed cases, but it's possible if you know your mole ratios of each of the compounds in your mixture. Yeah, definitely.
Thank you for your talk. So you mentioned that you use a implicit solvent model to model the aqueous phase. So I was curious that when you simulate the mixing phase between organic and aqueous, how do you treat the boundary layer between the organic and aqueous, or do you also use a cavity to describe the organic phase?
So it's not really a simulation; it's this statistical thermodynamics calculation, and there is no interface. Like it's not considering the interface, so it's basically just like bulk, two different things.
Okay.
And our next speaker is online. Kari Lehtinen is a professor and dean at the Faculty of Science, Forestry and Technology at the University of Eastern Finland. And his long career has focused on aerosol theory and modeling, as well as transport phenomena motivated by various applications in climate change, health effects of air pollutants, and nanomaterial synthesis. And today he'll talk about modeling uncertainties of aerosol properties and processes.
It's 9 p.m. in Finland, but I guess it's still good morning to you. And I'll be talking about aerosol properties, measurements, processes, and with a big focus on modeling uncertainties. And here's the team. It's a combination of say aerosol physicists and inverse mathematicians. I'll start with some motivational slides. So this is a time series of aerosol number concentration measurements with time on the x-axis and particle diameter on the y, and the color indicates the concentration. And let's say the overall aim, whether this being in some atmospheric station or in a chamber, is to reconstruct the particle size distribution with uncertainties, and also estimate process rates. Many times we're interested about nucleation, condensational growth, deposition, and those estimations also with uncertainties. And because we are interested in uncertainties, we have to look carefully what the instrumentation is doing. So we need to model the instrumentation also carefully. So this a typical number concentration distribution. This is taken from the Hyttinen station. And why I'm showing this is that typically these distributions are shown by single points or lines. And there's typically no uncertainty estimation of these size distributions. And what we are aiming at is something like this. And sorry about the hand-drawn uncertainty bars. So for each measurement point, we would like to estimate an uncertainty so that actually each measurement point would be given by a probability density function. So for example, for this single measurement point, what we wish to do is we would like to have the measurement giving this kind of a result, so that we would have the maximum somewhere at 7,000 and something, but we would also get information, what is the uncertainty, what's the probability density function of this measurement. And this is kind of what we're aiming at for single measurements. In the literature, you can see these type of pictures where you have uncertainty bars, but then these uncertainty bars typically show the range of different measurements over a certain time period. But we are really trying to do this for single measurements. As an example, I'm showing here a typical DMA, a very, very standard measurement device, which classifies the aerosol based on electrical mobility. So aerosols are charged, then they are brought to a kind of a chamber-like device where there's an electric field, and then the charged aerosol move in that electric field. And then they are counted, collected, and counted, typically optically. And by varying the voltage, you can always select a different size. And to somehow figure out what the actual size distribution is, you need to know how this charger behaves. So you need to know the charge as a function of, or the charge as a function of particle size. And what we have been trying to do now is to find out how uncertain these charging probabilities are. Charging is not the only uncertainty in these types of measurements. There can also be diffusion losses for some particle sizes. The counting statistics are very low, but the charging uncertainty is probably maybe the biggest uncertainty in these types of devices. And without going to any equations, how we have modeled this charging process is that we follow the procedure outlined by Lopez, Iglesias, and Flagan in 2013, where you first specify ion properties, then you use Boltzmann statistics for ion distributions, calculate flux coefficients, and then from these flux coefficients, so fluxes of ions to aerosol, and then solve the population balances. And by doing this, we get charging probabilities for the different charging states as a function of particle size. And by charging states, I mean, then we will know how many particles of charge, one elementary charge, there will be two elementary charges, and of both polarities. This type of an analysis was done already somehow by Fuchs, but let's say the first very good, say, model about this process was done by Hoppel and Frick in the mid-80s. And after that, Ali Wiedensoler curve fitted the data. And actually, these curve fits are still used in most instruments to date. The problem with this approach is that in this model, only a single type of charging ion was assumed. And in this figure, we have the mobilities. So mobilities of the positive ions, mobilities of the negative ions of different chargers. And all these points are different measurements done already starting from mid-70s up to something like 10 years ago. This was collected by Tigges et al. In 2015. And the ion that Hoppel and Frick was using and then further curve fitted by Ali Wiedensoler is here. So positive ion mobility about 1.6 and negative about 1.35. But as you see, there's a big variation in the ion properties. And what we have done is we kind of highlighted this range of these properties with this yellowish color. And what we then did was we randomly sampled a big number of different ion properties and then repeated the calculation that Lopez, Iglesias, and Flegan did, or earlier what Hoppel and Frick did. And what we get is something like this. So here on the top left, we have the charging probability as a function of particle diameter for charging state +1. Here, -1. This is +2 and -2. And of course, we had similar curves for all the other charging states also. The Wiedensoler curve fits, I hope you can see them. Unfortunately, they are very pale, let's say, kind of whitish pale dotted lines here in the middle of all these curves. But the big message is that there's really quite a variation in these charging probabilities. So if an instrument uses these Wiedensoler curve fits, and if actually the charging ion is something with very different properties, you can have quite a big error probably in the results when you invert the size distribution. Okay, let's go to process rates then. There has been lots of work trying to figure out formation rates, growth rates, deposition rates, and so on from size distribution measurements. And still many times, very simple methodology is used. For example, here is a very simple example. We have here from some measurement, the total number concentration as a function of time. It could also be a number concentration in some size range, let's say below 20 nanometers or so. And then we just look what the slope is during a nucleation event when the number concentration increases rapidly. And from that slope, we get an approximation for a particle formation rate. Or we can fit this line and then get time-dependent formation rates, or something like that, or something a bit more sophisticated. For growth rates, people have used also very similar methods. So here's this very typical contour plot, and you see a nucleation burst occurring here, and the nucleation mode grows. And if you follow, for example, the midpoint of the nucleation mode, or the front edge, or different methods have been used, or you can fit this with a mode and follow the peak. And then you can somehow estimate the growth rate. What we have been trying to do is use Bayesian methods, and the first choice was these Kalman filtering, Kalman smoothing techniques. And just for those of you who haven't heard so much about these methods, they have been widely used in process control and tracking systems, also in meteorological predictions. It's really an algorithm just really designed to estimate system parameters, especially those that cannot be measured directly, and very suitable for data that's inaccurate, or you can even have missing measurements. And as an output, you get something that's less noisy, more complete, and you also get, as a bonus, uncertainty estimations. The system parameters are modeled as probability density functions or distributions, and you can integrate physical knowledge and intuition in this framework. I'll say a few words about that in a while. So mathematically, in short, it looks something like this. Let's say we have a sequence of measurements. When you talk about size distribution measurements, they can be counts, they can be voltages or something like that. Then we have a state variable. So we have the number concentrations of size classes. Then we can have growth rates, deposition rates, nucleation rates. And then we have the model. We have some kind of an evolution model. For aerosol, the natural choice is the general dynamic equation. And then we have an observation model. So that basically models the instrument. And the problem statement is such that if we are given the measurements, so for example, the voltages, then we should be somehow estimate this vector x, which includes the size distribution data and also the unknown parameters that we are interested in. In terms of terminology, if we use data that's before the time interest that we are looking at, we talk about prediction. If we use data up to the time t that we're interested in, we talk about filtering. And if we use also data after, if we have a time series and we want to find out data in the middle, but use all the data, then we talk about smoothing. So if we use these Kalman techniques, we talk about Kalman smoothing. Okay, then how we use physical knowledge and intuition. In this case, the natural choice for the evolution model is the aerosol general dynamic equation. You all know about that, so no need to go through it. And what we can use in addition is guesses for the variables so that they make sense. So these Bayesian methods, they are based on the Bayes formula. So where we have a prior, which at the first step we have to guess. And let's say, for example, that we know that the number concentration must be between 0 and 1 million per cubic centimeter. Then we can input that data in the initial guess. We can, for example, limit the probability density function of the number concentration in that range. Or if we know that the growth rate will not exceed 20 nanometers per hour, we can do the same thing for the growth rate. Then we can also introduce correlations, both in time and size. So let's say that you are looking at time evolution of a number size distribution of an aerosol. It's very likely that there are not dramatical changes as a function of size or time. So you can introduce correlations, let's say, for example, between successive time steps and successive size bins. And once again, just to remind of the problem statement, this is again the general dynamic equation of aerosols. And basically everything is unknown. We don't know the number concentration, we don't know the growth rate, the coagulation rate, if we want to make it unknown, deposition rate, and I didn't put nucleation here, the J, because in our way of modeling this, we use we put nucleation as a boundary condition, so it's not in the GDE itself. So if we have the sequence of measurements, voltages, counts, whatever, then by fitting this optimally, we somehow should be able to figure out all of these unknowns. And I'll just show a couple of it. So actually one example of this, we have tested this methodology with several synthetic measurements, and it seems to work pretty nicely. Here I'm showing the application to a particle formation experiment done at Cloud in CERN, where as a function of time, we have the time evolution of the number concentration function. So here, nucleation starts, and then the particles start growing, and we approach something almost like a steady state distribution. And the measurement device here is something called DMA train. So there's 7 separate DMAs, all tuned to a certain size, and they don't cover the whole size range. So there are gaps, but for this methodology, it doesn't really matter. And in this case, we have used Kalman smoothing to figure out the formation rate, the growth rate, the number concentration function. And in this case, I'm just showing here the formation rate as a function of time, here in yellow with the uncertainty, and just comparing with some previous analysis done by the cloud research community with different methods. And here the same for the growth rate as a function of size at a certain time. So in yellow, this fixed interval Kalman smoother, best estimate and uncertainty, and in green, the same analysis done by a method called InSide by, I think these were Austrian scientists taking part in these cloud experiments. Then finally, I would like to show a very, very separate example of inverse modeling. One of the scientists in our group is an expert in Markov chain Monte Carlo methods, and that seemed to be a very suitable method to analyze a case like this, where we were studying, or actually a group in Tampere University was studying tailpipe emissions of a car, and they measured it with an engine exhaust particle sizer after some tubing. And what we wanted to know was that if we measure the size distribution evolution here, what's the actual emission coming from the tailpipe? And one of the things making this difficult is that these emissions from a tailpipe, they are non-spherical, so very irregular particles. So we had to model the coagulation coefficients using this fractal theory. So we had the fractal parameters, fractal dimension, primary particle size as unknowns or uncertain variables. Also, van der Waals force was unknown, so we perturbed the Hammacher constant. And there was also some uncertainty in the flow velocity measurement. And what we got for some measurement was something like this. The measurement with the EEPS is here given in yellow, and then the inverse calculation produced a curve like this in blue. So from the tailpipe, there's more aerosol coming out, especially in the smallest particle size ranges. And what happens during the sampling through these tubing lines is that these particles collide with the larger ones, so making the number concentrations of these smallest particles lower. Then this is just the probability density functions of the previous slide at 10 nanometers. So we looked at all these uncertainties of the variables separately, but also together. So here, this red curve shows the variation or the probability density function at 10 nanometers. So about here. That's it. Here are the papers that describe some of this work. The one in the low left corner is still in submitted status. We got the referee comments and are now about to answer them. So thank you.
Thanks, Kari. Questions? Well, I can ask a question. You showed the estimated formation rates and growth rates with the uncertainties, and there was comparison to this InSight method for assessing the growth rate from measurements, but I believe that's not the most common method for growth rate estimates. So how does it look like for other approaches that have been used? Have you tested?
We didn't really test. The reason we used this method here was that we had scientists collaborating with us who actually made this InSight method approximation of the growth rate for this, or originally for this cloud campaign. So that was the reason.
Okay.
So the answer is no, we didn't try any other methods.
I was just saying that this is within the uncertainties, but I was just wondering if other methods could give different results.
Yeah, good question.
We have another question, Nicole. And first, Ken.
I have the mic. Hi, Kari. It's Ken here. I have a question about whether you plan to kind of reprocess the global observations to get our nucleation and growth rates, because, you know, as you know, we evaluate global models against particle concentrations and very rarely growth rates and nucleation rates, which would be a much better constraint on the models. And we'd like to use that. Are you going to apply this turnkey to the whole data set available?
If we get suitable funding for that, but let's say that we will start with some special cases and maybe analyze a bit more of the cloud data available, because that's kind of the cloud data is somehow better behaving, and the method works at this point better for chamber data than let's say atmospheric data that varies a lot. But we will definitely analyze a bunch of atmospheric data also. Maybe not all available, but some.
Hello, Kari. This is Nicole Riemer from the University of Illinois. This is very interesting, and I was wondering, sometimes coagulation kernels are actually not very well known, especially if you think about turbulent environments, and maybe this pertains more to cloud physics, but may also pertain to aerosol systems. So would you be able to back out coagulation kernels with these kinds of methods, and what kind of measurements would you need for that? Is that possible with point measurements in the atmosphere, or yeah, can you help me to understand that?
Yeah, yes, definitely we can. One thing I didn't mention is that in this analysis that we did in the cloud experiment, we assume that the coagulation coefficients are known. But in this one, we had these uncertain fractal coagulation coefficients. And at the same time that we get the estimation for the particle size distribution, we also get the best estimates for the coagulation coefficients. So the answer is yes.
Great, thank you.
Okay, if there are no more questions, we'll thank Kari again.
Thank you.
And then the last speaker of the session is Laure. She's an earth scientist in the Atmospheric Sciences and Global Change Division at the Pacific Northwest National Laboratory. And her research focuses on advancing the predictive understanding of aerosol effects on clouds and radiation through improved representation of multiscale aerosol processes. And she specializes in particle-based methods for simulating aerosol size composition distributions through the development of quadrature-based moment methods and the application of Monte Carlo methods. So please, Laure.
All right, thank you. So yeah, I'll be presenting a few different studies here that have been done in collaboration with many different people over the years. So as I'm sure this community knows, aerosol effects are a large uncertainty in a large source of our uncertainty in our predictions of effective radiative forcing. And so one reason that atmospheric aerosol particles are so difficult to represent is that aerosol is contained in distinct multi-component particles. So this is fundamentally different from things in the gas phase, right? So we don't need to know just how much of something there is in, say, a grid cell, but we need to know how that aerosol material is distributed among particles of different sizes, having different chemical compositions and having different morphologies. And so this makes modeling atmospheric aerosol very difficult, as I'm sure this community well recognizes. So just to make sure we're all on the same page, when we're modeling aerosol in large-scale models, when we're specifically modeling the evolution of the particle distribution, I should say, it typically comes in one of two flavors. We have our sectional schemes, which are shown on the left, where we take the size distribution, divide it into bins, and track the amount of stuff in these different bins, assuming that particles within the same size bin have the same mass fraction of the constituent species. The more commonly in our large-scale, long-running global climate simulations, we use a modal framework where we divide particles into different classes, where each class is assumed to be a log normal distribution having a fixed standard deviation. And again, we often assume that those particles have the same mass fraction of the constituent species across that population. And importantly, we do fix that standard deviation. So that's not necessarily something we need to do in our modal models, but it seems to be what most people are doing right now. And so at the other extreme, we do now have a particle resolved model, part MC mosaic, that tracks the full dimensionality of that particle size composition distribution. So if we have 20 aerosol species, our true aerosol population would be described by a 20-dimensional probability density function. And so this is impractical to simulate by, say, binning the population in each dimension. And so instead, this model uses a Monte Carlo representation, simulates tens of thousands or more particles, and has been shown to converge to analytical solutions if enough particles are simulated. And so this is all very nice and all, this very detailed model. But right now, it's really not practical to incorporate this level of detail in our climate simulations. And so we have this issue where we have these reduced schemes that are sufficiently computationally efficient that we can run them in our large scale models. And then we also have this very detailed model, which is likely far more accurate, but is too computationally expensive to be used in these big models. So what we can do is use this detailed model to figure out how well those reduced aerosol schemes that are more typically used in the large scale are representing the things that we care about. And so very briefly, I'll go through a couple of examples just to illustrate two different factors that I've been looking at over the years. So one is the simplification of the particle mixing state. If you assume that all these particles are identical across these different modes, what sorts of errors pop out of your solutions? And then Also, more recently, I've been looking at the simplification of particle size distributions, specifically with the modal aerosol model. Let's start first with the impact of simplifying the particle mixing state. So I'm going to focus first on light absorption by black carbon, one particular aerosol species, one particular problem. And so we all know aerosol overall has a direct cooling effect, but black carbon in particular is strongly light absorbing. In fact, it's so absorbing that it's now estimated to be second only to CO2 in its warming impacts on the climate. And so if we want to know how much light black carbon is absorbing, what the radiative impacts are, we need the optical coefficient in each of our model grid cells. And so really what this would depend upon is the integral over the optical cross sections of these diverse particles within the grid cell, which of course we don't track all of the detail to know exactly what those optical cross sections are. So for example, if we use an approximation that is common in our simulation of atmospheric aerosol, and we assume that particles within a mode have the same composition, and I should note this is if we go ahead and separate the BC containing particles from the rest of the population, which is actually something modal models don't tend to do. But if we were able to do that, and we would say if you increase the coding here, oh, okay. To work. Okay. So if you increase the coding, the amount of non-absorbing coding on the black carbon going from left to right, the absorption by those particles is increased relative to an uncoated sphere. So this means that if you have your particles contained in the same, you're not absorbing and you're absorbing stuff in the same particle, you end up with greater light absorption than you would if they were contained in separate particles. So unfortunately, when I guess it's been a few years now back, when we compare this with ambient observations, we find that this model doesn't work very well. We find that the absorption that we would predict from our common approximations of light absorption, given our approximations of composition, we end up with much higher light absorption than we would expect based on ambient observations. So we'd like to know what's going on here, right? So one thing that's different between these populations is the fact that real particles have come in all of these different shapes. They're fractal, black carbon in particular. The coatings can be distributed in irregular ways. And this is not something that we represent in our models. Instead, we typically represent our black carbon containing particles as a concentric core shell configuration, where you have a spherical black carbon core that's coated with a uniform coating. Okay, so some of my colleagues here on this paper, they went into the laboratory and they decided to investigate this approximation through some detailed laboratory experiments. So they took tremendous care to generate the black carbon in a realistic way and coat it with non-absorbing coatings. And so what we find is that this doesn't really explain this difference between the observations and the modeling, right? So we see that there's a bit of a difference for very thinly coated particles, but as the particles become more thickly coated, this core shell approximation seems to work pretty well in comparison to our laboratory data. So this is not really explaining what's going on here. But there's another way that particles are simplified, and that is the fact that particles are compositionally diverse from one another, right? We have all these particles in a population have coating that's of varying amounts of coating, and it tends to vary with size, and these particles, this variability in composition is just not resolved in our population average composition. And so if we go back, and so what we did here is we used the particle resolve simulation to perform ensembles of simulations, because this is not something that we can explicitly measure in the atmosphere very easily. So we performed many, many simulations, and in order to better understand how absorption should vary with the average composition of the population. And so we did this, we performed many simulations, varying aging conditions to represent a wide variety of conditions, and then analyzed all of those different populations. And so what we end up with is thousands of aerosol populations. Then we can then make predictions of the light absorption as a function of the coating thickness, given the variability in those particle populations as well. So if we go back to this little schematic, so in the case of our laboratory measurements, as well as our default modeling, we're assuming this uniform composition across the population. So in our laboratory measurements, by design, we size select these particles, coat them so that the particles are uniformly coated. So we're not representing this diversity in composition intentionally. And so in our more realistic simulations in the real atmosphere, we would assume that these particles are compositionally diverse. This is what we would expect. And so then when we use this improved model that accounts for the particle-to-particle variability in composition, as well as a modified per particle absorption based on the lab measurements, we find that this agrees much better with ambient observations. So this suggests that if you want to model that black carbon's light absorption accurately, you really need to account for the fact that these particles are compositionally diverse. And this is something that's just not practical to do explicitly within large scale models at this point. So we know that in this particular case, the resolution of the mixing state is inadequate. This also causes problems for CCN activity. I won't be showing that now, but this is some work that we've done in the past. So what about the size distribution? How well are our models doing representing the evolution of the size distribution across these global schemes? Because in many ways, this is what they were designed to do, right? So I'll be giving an example here of how we use this particle resolved model to benchmark a reduced aerosol scheme. And this is a set of scenarios that I'll be presenting. I'm hoping that we can refine this approach and choose a standard set of verification tests and standard set of metrics for evaluating accuracy and efficiency of these models. But for now, I'll just be giving a simple example of aging by condensation and coagulation. So just a reminder, we will be talking about this at lunch today. So I performed about 100 scenarios of MAM4 and part MC at the box model level. And so the input parameters for these scenarios were sampled from E3SM, DOE's global climate model, and we also varied the condensation rates to agree with the span and condensation rates one would expect from observations. And so you can see going from left to right are the simulation results as a function of time, and this is just 5 example scenarios from that ensemble. And so you can see that there is quite a bit of difference here between the part MC and the MAM4 simulated size distributions. And what I'll show you in a second is that this really depends on the aging conditions. So this very bottom row here, you can see that there isn't really so much difference between MAM4 and part MC. And the reason for this is an example of a case that's rather pristine. There aren't a lot of particles, there's not a lot of stuff condensing, so really nothing's happening. Both part MC and MAM4 are staying very close to the initial conditions. And so if we lived in a world where nothing happened to the particles, we could do a really good job with some of these reduced aerosol schemes. But if we actually want to simulate a case where the particle distribution changes, MAM4 does not seem to be performing very well. And so we went through and we quantified the differences in those distributions using the KL divergence, which is just a metric of distance between 2 different distributions. And so we looked at these same scenarios with coagulation only and condensation only. And as one would expect, the faster the aging rates characterized by the number concentration integrated over time or the integrated condensational growth rate, we find that those differences increase the more aging that those particles experience. So do these differences in the size distribution matter? I would say, in fact, they do. This does also lead to a big difference in their CCN activation properties, which again is shown here from for these 5 different example of scenarios going from left to right. So again, in that very bottom case where nothing's happening, the CCN activation is doing pretty well. But in those other cases where the particles are aging, we see that the differences between part MC mosaic and MAM4 are quite large. And so it's actually quite difficult to quantify the error at a particular, in this CCN activation problem, because if you choose a particular supersaturation, it sort of depends on how big the particles were in the first place. And so the way that we've quantified error in this case is looking at the threshold supersaturation that is required to activate a certain fraction of particles. So that's what I'll be showing here in just a sec. And so you can see that what's shown here is across our different scenarios, the KL divergence, which is that metric of distance between the two size distributions, as a function of this onset supersaturation required to activate a certain percentage of particles. So green is showing this ratio between MAM4 and part MC to activate that fraction of particles for 99% of particles, and then the blue is showing 1% of particles. So just looking at a range of the distributions there. I understand that this quantity is a little bit difficult to digest. So for example, if this ratio between the threshold supersaturation for 99% activation is 5, that would mean that you need to increase the supersaturation by a factor of 5 to get this agreement between the two models. You'd have to, and so in all of these cases, or not in all, but in most of these cases, MAM4 tends to require higher supersaturations to activate the particles. And then again, taking this back to our aging regimes, looking at just one of those onset supersaturations, we can see that the differences in the CCN activity again depend on the aging conditions, which we've here characterized by different regimes. So in remote regions where things are happening very slowly, this isn't a major problem, but in our urban areas where the particles are aging quickly, you can see that the CCN activation quickly diverges between these two. So, oh my goodness, I do not have very much time. I'm going to breeze through the last of this. How well do these aerosol schemes represent our particle properties? Well, in many cases, not very well. Can we do better? Yes, we can. So I do want to emphasize that we've actually done quite a lot of work in our community that I think that we can leverage to move forward with this problem, right? So we have a lot of great work done at the particle scale, where we're using laboratory measurements to inform our particle scale models, and we've heard a lot of great talks about these mechanistic simulations that have been advanced over time. We also have a tremendous body of field observations that we can use to evaluate and constrain our global models, and various methods for doing that have been led by people in this community. But a key missing gap here is a way to bridge this particle scale to the population scale, to the global scale. And so one way to do this is using surrogate models, which can be done using some sort of regression or machine learning methods. And I'll just quickly show that the idea here is we use lab-informed modeling to inform our per particle properties. We could use thousands of, many simulations with something like part MC mosaic. And we've done this using, in this case, just a kernel density regression to come up with an improved prediction of absorption enhancement, which we applied to the GISS model. And we can see that when we do this, we can get really big differences between our particle to particle varying simulations as opposed to this uniform composition approximation. And this just uses the information that's already carried by the global model. But the key here is that these models really need to track the right information. So if you're not resolving enough information about the mixing state that you know how many particles are mixed with BC material, in this case, you wouldn't get a good prediction. If your model takes as input something like the size distribution parameters or moments over a distribution, and those parameters are not simulated accurately, again, this won't work very well. And so what I've been advocating for, in addition to using this sort of approach to represent properties that we cannot resolve, is the introduction of these quadrature-based schemes, which I'd be happy to talk about later. I don't have a lot of time to discuss this now, but the idea here is that we would have a better representation of the distributions intentionally designed to carry the information that we care about in our surrogate models. And these quadrature-based schemes are briefly just an efficient representation of the size distribution. So binning these high dimensional distributions in like a sectional scheme quickly gets computationally impractical. So these quadrature-based schemes can be thought of as tracking representative particles that really carry the information about the moments of the distribution. And the key here is that this quadrature approximation very accurately represents moments over a distribution. And I'll skip over this. I think this community probably knows what a moment is, but basically you you can take any sort of function here in the middle, and it'll produce the integrals over the PDF in high accuracy and comparison. And then when we do this and we reconstruct our distributions, we find that this works really well. It can accurately represent the evolution of those distributions. And really what it comes down to is accurately representing the moments. So sorry to breeze through that last part so quickly, but I think that this is actually an optimistic message. I think that we do have a path forward, leveraging the things that we're already doing. And so I will just close by saying, I think really the key here is this bridge between scales. And I think this involves both surrogate models, which we've been advancing very quickly, as well as better representing our distributions. So thank you. I want to acknowledge my funding. Thanks to PNNL for a lot of internal funding for the things I've been presenting. And then also please reach out to me if you are a graduate student or if you have a graduate student. DOE and PNNL in particular has a lot of great programs for graduate students. And then just a final reminder to please join us at lunch if you're interested in verifying your aerosol scheme. Thanks.
Thank you. Other questions to Laura?
Yeah, this is absolutely fantastic. I hope we can make better models as a result. Years ago, we compared a good bin resolved model with a modal model with the same driving physics and chemistry. And I was surprised how similar they were, which then led us to adopt the modal model because it's simply computationally feasible for climate simulations. I wonder whether box model tests of these kind of things have a tendency to identify pathological cases that don't actually occur very often in the real model when it's running with advection and mixing and deposition and all of these things that are going on, which you don't have in a box model. It's only sort of anecdotal in that when you compare bin and mode, they look very similar. And therefore I wonder, why you find sort of pathological cases like that. Are they really useful to identify?
Yeah, that's an interesting point. And I'm familiar with that paper. It's very nice work. Thanks. I do think that is one thing that we're hoping to do when we design these verification tests. Think if there's some way that we can do this so that we aren't identifying those cases that are maybe not representative of the real world. I don't have an answer. I don't know why yet that's the case, but I do hope that you'll join us at lunchtime to discuss what kind of verification tests we should use.
Part of my question was kind of similar, and I think the more processes you have on at once, the more it kind of smears things out. But I was kind of curious in this isolated case where I'm guessing it was just condensation and coagulation happening. Do you know for the modal scheme, you were able in the part MC, you really got the scrunching of the growing Aitken mode. And so I'm wondering how much of the error in the modal scheme in that case was due to the fact that the log normal mode width is fixed, or how much is due to the force transfer function that as your Aitken mode is growing, it's just going blah, 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 up.
Yeah, I actually think it's a function of both of them. So I have performed simulations with this quadrature-based method using 1-point quadrature, which is effectively the same as a modal model that runs with a 2-moment scheme. And we don't find as big of differences. I mean, obviously the simulation is too broad, but it's not, I think there's also something else happening that maybe these models, even given the current framework, could be improved upon a little bit. So in MAM4, at least, when you look at the geometric mean diameter around the globe of a certain mode, it's basically the same. They move things between the modes to force the geometric mean diameter to remain the same in the different modes, at least in the implementation as done here. So I think the mode, somebody's discouraged us using mode merging, maybe mode reallocation or whatever word we should be using right now. I think that's actually a bigger problem than we've previously recognized. But obviously, assuming a fixed standard deviation is also going to cause you some problems.
Thanks.
2 questions. The first one is, how was the volume of black carbon and the volume of coating determined for the fractal shaped particles?
So we didn't actually simulate fractal particles. Those were based on laboratory measurements where the particles were generated in such a way that we would have expected at least some of them to be fractal. But in the case of the ambient observation, Chris Kappa is sitting in the room, so he can correct me if I'm wrong, but they use some sort of denuder system to evaporate the coating. And I don't actually, can you please weigh in here?
Yeah, we've done it in two different ways, evaporating coatings or comparing to mass absorption coefficients at the lowest coating to black carbon ratios and reference that. So there's two ways and they give about the same result.
And in our case, we always do dry. We've been simulating these as dry particles to be consistent with the measurements. We can follow up offline about some of those technical details.
The other question is it straightforward to figure out the size and the chemical composition distributions from the multi-dimensional quadrature point methods?
So not necessarily. In some, if you have a univariate distribution and you use something like Gauss-Hermite quadrature, yes, like you still have it separated by modes and you can reconstruct those very easily. We actually spent quite a bit of time figuring out what we should do with these higher dimensional distributions. And so we ended up using maximum entropy distributions, which is described in our 2017 paper. And again, happy to follow up with you. I know I've gone over time.
I'm trying to figure out a way to formulate this question, but it's probably unlikely that we would be able to represent the particle distributions with just one composition per bin or mode. But, when I was thinking, when you showed that comparison, is that when we do try to do that, we weight everything just by mass, I think, right? So it's just a mass weighted. And then I'm trying to think about, is it better to weight by another property that better represents what you're trying to represent? So, do you need into account the hygroscopicity distribution or something else and weight your distributions if you're trying to predict CCN activity?
Yeah, so that's actually one thing that we've done a little bit. We've used projected composition rather than, we don't have a quadrature approximation of the full 20-dimensional distribution simulated by PartMC, for example. We did this using a 2-dimensional dry diameter hygroscopicity parameter representation, and then use that to project and compute the CCN activation curves. But yeah, there's a lot more thought that needs to go in here. I think we need to go through the exercise of figuring out what level of detail we really need. And I think such verification tests could be really helpful for helping us do this. It looks like there aren't any more questions. So I think and I went over time, so I apologize for keeping you all from lunch.
Thank you, Laura. So let's thank all the speakers again.